Good morning, everybody. My name is Karina Mendoza, and my team and I will be presenting our COVID-19 surveillance system with facial recognition framework. On the following slide is the outline of our presentation that highlights the key points we'll be discussing, which includes the team member introduction, project motivation, project description, our design for both hardware and software, the bill of materials, our demonstration, our video demonstration, and with the accompanying website, our project completion, future work, and standards and constraints. So let me start off by introducing the team members who will individually be introducing themselves throughout the presentation. So we have myself, Karina Mendoza. I am the team leader and I am majoring in computer engineering. We have Ahmed Jaber, who is our hardware lead, majoring in electrical engineering. Joe Lanzi, our software lead, majoring in computer engineering. And then we have Anina Bofamonte, who's part of the software team, who's majoring in computer engineering, and Brandon DeLeo, who's part of the hardware team, majoring in electrical engineering. So our main motivation for our project is the impact that the coronavirus disease, also known as COVID-19, has made to the Norman society. In the US alone, the CDC has reported 31.9 million cases, which changes drastically daily. So because of how quickly the virus spreads, we were inspired to create a product that will assist with the building protocols already established within Manhattan College. So after considering different alternatives, we found that our security surveillance system was the most desirable option, which you can see on the next slide, to ensure the safety of others. Our plan was to create a small but feature-packed device that can be monitored wirelessly to track the movement of everyone coming in and out of the building to ensure social distancing. And many people are unaware that they fall under the threshold of having what identifies them of having the virus. So this device will be able to obtain as much information to identify such an event by implementing body temperature monitoring and a fully functioning facial recognition software to identify those with high temperatures and alert the authorized personnel. And all of this data will be collected, can be viewed or accessed through a website that was created solely for our system.
So in this slide, we'll talk about similar researches that was done in the past. Due to the ongoing pandemic, the implementation of contactless smart thermal scanning equipment, as well as facial recognition technology, is on the rise to support people who might have the possibility to be diagnosed with COVID. Based on the table that we are seeing on the screen, most researchers have designed their system to measure body temperature and detect people who might have a high temperature based on artificial intelligence and advanced thermal detection system. For example, a group of researchers and STD from Thailand is using LiDAR to differentiate the body temperature of an individual human being in a group. Now, what makes our system different? It's way cheaper than any other system mentioned on this table, easy to implement. The whole system is compact and portable, takes around 10 seconds from measuring temperature to detect human face and post all the information in a secure environment. Next slide.
This is the behavior module of our system. It shows our sensors and our camera taking in the data and going to the microcontroller. And when the temperature is too high, it will be displayed on the LCD display and ran through our facial recognition. And then that data will be sent to our database, which is then displayed on our website. Here's the system architecture for our system, which basically just shows what each part of our system is connected to and what it's doing.
At the core of our system, we have ESP32 microcontrollers for data processing and transmission. For data collection, we have the ultrasonic sensor with range up to 400 centimeter, PIR motion detection sensor with range up to 6 meters from the sensor, a 5 megapixel ArduCam camera module with 90 degrees field of view coupled with microSD module for data storage, and an LCD display to showcase instant body temperature. Next slide. This is our occupancy counter subsystem. The algorithm that's been implemented on this subsystem can be seen from the flowchart diagram. Basically, when the motion sensor detects motion, it wakes up the two ultrasonic sensors, and depending on whichever triggers first, it determines whether a person is leaving or entering the building, and likewise add that number to the count of the total occupancy of the building, and then send the data to a Google Sheet to process it, and then later on display it on the website. There are two subsystems connected together, as you can see on this picture. The image capture and the temperature sensing subsystem, they're both connected together. The way it works is that when a person hovers their hand or palm, the IR temperature sensor measures their body temperature, and if that temperature is higher than the threshold temperature, which is specified on the algorithm, a red LED will turn on, which will prompt the camera to take a picture of that person, store it on the microSD card module, and later on send it to a Google Drive folder for facial recognition algorithm to run on it. The temperature, it also goes to a Google Sheet for further processing. The temperature data then also displayed on the LCD display as well as on the website along with the identified person.
And so this is pretty much the entire system of the software architecture. But data is collected from the ESP32, what Ahmed was talking about, and it's then automatically processed to the database with the facial recognition. And that's all shown in the website within just a matter of 1 second. And so the following is actually a short demonstration of how this automatic file handler operates. The system architecture begins at the hardware and the sensors. Once the hardware outputs the data, it is then wirelessly transferred to the temporary folder of the database. From here, a system handler was created after a first in first out queue to consistently monitor the temporary folder. The system handler is capable of automatically applying the facial recognition algorithm to the image files and moving the updated data into the database. Once in the database, the local IIS web server will consistently run an HTML request once new files have been added and show directly to the website. A website consisting of HTML, CSS, JavaScript, and PHP are port forwarded using an IIS to be accessible worldwide. Here is a simple demonstration of the software architectures working together. Once the image and the data files have been dropped into the database, the system handler executes necessary instructions and outputs them. Afterwards, the web page displays all the newly acquired data using JavaScript, PHP, and HTML requests, which is all accessible worldwide in just a matter of seconds. And so next, with the COVID cases on the rise in 2020, of course, our group decided to equip our system with the facial recognition technology. And so this is a short video composed of the following stages of progression we've taken to apply the facial recognition to identify individuals with facial coverings. Modern facial recognition software is a form of biometrics that map facial features called landmarks or nodal points from a photo or a video. These landmarks include the distance between the eyes, width of the nose, depth of the eye socket, distance to the forehead from the chin, and 100 more different measurements. All these are converted into the individual's facial feature using mathematical formulas. It is then compared to a database of known faces to find a match. One of the very first steps of facial recognition is the process of image segmentation to locate the region of interest, which in this case is to locate the coordinates of a face within a 3D space. This process mimics that of a person when locating objects within our peripheral vision and making mental notes of their location. This task can easily be accomplished using deep learning, which in this project, two methods were used to get fast results and quality results. Histogram of oriented gradients is a feature descriptor used to provide visual features of the contents in an image, video, algorithm, and applications which produces descriptors like facial features. Its main goal is to convert an image into a feature vector that can then be used in image recognition and object detection. This descriptor calculates the distribution or histogram of oriented gradients by using a horizontal or vertical gradient filter using Sobel operator with a kernel size of 1. Once the gradients are calculated within an image, the gradient magnitude and directions are calculated using the following mathematical formula. The next step is to apply this method to the entire image by dividing the original image into a small 8x8 patches, which then returns a 3-dimensional vector feature based on the magnitude and direction values. By converting facial patterns to a real value vector to represent the basic structure of the human face, it can then be used to extract the coordinates of similar vector values within a new image. One of the problems with this method is that the face must be as centered as possible for the algorithm to be utilized. To account for this, a facial landmark estimation algorithm is used to warp the vector values as centered as possible, even if the face is looking in a different direction. Its basic idea is to use a series of cascade shape regressions to transfer specific points of the existing face into landmarks. These landmarks capture the pattern calculated in the whole face, including the small features, and simply rotate, scale, and shear the image so that the features are centered as best as possible by using affine transformation without introducing any distortion. Although that method of facial detection is accurate 98% of the time, it can easily misclassify and sometimes not locate faces due to unaccounted circumstances. And so to vastly improve the accuracy, a modified brute force method is used in conjunction with a faster method. This is called a regional-based convolutional neural network. The backbone of this deep learning pipeline involved Felsen-Schwab superpixel generation method, which creates a selective search algorithm that filters an image by utilizing a series of equations that divides an image based on color similarities, texture similarities, size similarities, and fill similarities. Regions of proposal candidates can be then created by using a merging equation to create a single component. The RCNN is then trained in tandem with the data collected from the histogram of oriented gradients, with a model consisting of convolution, pooling, comparisons, and 50 other dense layers, which equates to millions of parameters for the deep learning network to train with. Once the face is detected, it is then transformed into a 128 array. The more data collected from one person, the more keys can be used to identify this person. Once a database of a person's blueprints have been created, these are then saved as pre-trained weights for the classification. When a facial detection recognizes a face within a new image, it is then compared with the database landmarks to identify the face. Then, the RCNN is simply defined and trained with this numerous amount of data. One of the biggest problems in this project is that the algorithm must now be written to detect and classify individuals with facial coverings. To achieve a solution, we can investigate how the human brain has already solved this problem. Given the two images shown, our human brain can tell that these two images are of the same person. But how? The answer is simply that the facial features are still similar outside of the facial covering, and our brain can make a good estimation of the identity of that person. To account for the facial coverings, a facial landmark estimation can be rewritten to account for the missing features of the face and still make a good estimation based on the unblocked facial features, such as the eyes, chin, ears, and the forehead. Since majority of the data is now blocked from the facial covering, the data can be modified to account for the missing space by either upscaling the original image or making the kernel size smaller. With this method, we can create the same amount of vector values to classify the individuals. Here's a sample result from our deep learning method. And here it is applied to our faces.
Uh, for our integration testing, there are 5 subsystems, which 3 for hardware and 2 for software. And we've completed the occupancy test, the temperature reading test, the data storage test, the identification test, and the data transfer test was completed through our shared Google Drive. Here are 2 examples of our integration tables for the occupancy and data transfer tests. When implemented together, you can see how the occupancy test uses our travel direction algorithm to update the occupancy count in the database, and the data transfer test then ensures that this new data gets uploaded to the website. For the unit integration and acceptance testing, we have completed an iteration table to show the corrective actions taken to ensure that the system completes its functionalities. The entire table is pretty long, so this is a short portion of the iteration table showing the work done that we have. For the acceptance testing, we have 5 main engineering requirements. We promise a facial recognition software up to 98% accuracy, a module to measure body temperatures within 2 degrees Fahrenheit accuracy, and an overall fast responding system, which would include a short database processing time and a short website updating time. We were able to complete these requirements and have provided graphical results to demonstrate the dependency of our system.
So for the acceptance testing for the software, the final model with 50 facial features of people, it reveals up to a 98% accuracy, as well as an astounding 1 second processing speed with an average of 50 from the average of 50 iterations seen on the right side right there. And pretty much all of that happens in the background automatically. Next.
So the graphs from the acceptance test shows that the IR temperature sensor that we have used has a plus minus 2 degrees of Fahrenheit accuracy, which meets our engineering requirements. Now on the next slide, we'll see a demo video where the threshold temperature was set at 90 degrees Fahrenheit for demonstration purposes, which means that if the body temperature is higher than 90 degrees, the system will capture human face and record their body temperature to display it in a website.
This is our COVID-19 surveillance system with facial recognition framework. Here we have our IR temperature sensor, which can measure my body temperature up to 5 centimeters from the sensor. Now I'm going to hover my hand over the temperature sensor, and here, as you can see, the red LED has turned on, which means that my body temperature is higher than the threshold temperature. And then this 5 megapixel camera module, which has a 90-degree wide lens, has already captured a picture of me, and then stored the picture on this micro SD card module. And this data will be transferred to the Google Drive with the help of our microcontroller. As I move along, we can see this LCD display is showing my temperature, and then it's saying that my temperature is too high, and this data is also going to a Google Sheet spreadsheet, and then from there it will be transferred to the website. Moving along from left to right, as you can see, this is our capacity counter subsystem. Here we have 2 ultrasonic on both sides and a motion sensor in the middle. The motion sensor has a range of 5 meter and 12 meter, and it's already detected my movement. And the ultrasonic sensors has a range up to 2 to 400 centimeter. And based on the algorithm, since I move from left to right, I have entered the building, and this data is also going to the Google Sheet, and then eventually will be transferred to the website. When a user walks by, the data that is collected from our hardware will be sent to a folder in our shared Google Drive. There's one sheet dedicated to the occupancy count, which is shown here. Our date and time of when the user walks in is recorded, and so is the final occupancy. There's also a sheet dedicated to temperature that passed a threshold that indicates a fever, which is shown here, and this shows the date and time recorded as well and the temperature of our user. The image that was captured when a high temperature is detected is also uploaded here in this folder. The automatic system handler is implemented into the shared Google Drive, making it responsible for running our facial recognition and transferring our data. When the images are ran through the facial recognition, the pictures are then cross-referenced with sample IDs to identify the individual.
Once the hardware transfers the occupancy, temperature, and the image of the individual entering the building, the system handler will automatically process all the data into the database with a facial recognition. This will automatically update the database and show straight to the website within 1 second of receiving all the data. In the security page, we can see the updated occupancy increase and the data of the individual.
Okay, so before we continue with the rest of our presentation, we wanted to show you the demonstration of our website. So if you look at the chat, Joe has provided like the IP address to our website itself, but we're just going to show you how it looks. So Brandon can pull that up real quick. So here is the main page, which shows the occupancy of the building at the current time. So when we last did this, it was 12, and it updates in real time. You can see from the bottom, and whenever new data, whenever someone comes in or out of the building, it will automatically be updated. And on the next page is the about page, which just is like a brief summary of everything that has to do with our system, our location of where we plan on having it built, which is the Leo building, what our system is, the technology we're using, brief summary of the facial recognition software, explaining it, the advantages we have for our project compared to others that we've shown in our background research, the equipment used, and a quick introduction about the team members at the bottom with our LinkedIn accounts if you're interested. And then on the security page is where we have our database that's for security personnel only. And here you would enter the username and password. Brandon, can you put that in? Excuse me 1 second.
Yeah, that's not letting me type.
Is that letting you type it?
Mm.
Oh God. Okay. Well, I'm sure if everyone is click the link that's in the chat, you would enter the username and password, and you would see the same thing that we showed in the demonstration video, where we had the occupancy at the top, and it has a database showing the name, time, the name of all the individuals that were identified via the facial recognition software, their ID, the time that they came in, and their image on the side after the facial recognition was processed. I'm sorry, it's not working at the moment. But yeah, that is our website. And if you want on your own time, you can just visit it and you can just read all about our system. Yeah, we go back to the presentation then.
Okay, so based on the timeline created from our project proposal, we have completed our project on time and successfully for both hardware and software designs. But some future work possibilities include daily reset for the occupancy counting, putting together this system into a hard casing for durability and sustainability, and the testing of the system using the building of choice. For this case, we would be using Leo building. Next slide. So here's a short demo video of how we would have our system completed with our future work. And if we were to continue the work on this project, this would be an ideal look of the system. So you would walk past it at the door, need to get the temperature reading before walking farther into the building. And if the temperature with the LED display is high, then the picture will be taken, and but if it passes, then you're able to proceed into the building and the occupancy will update. And from the video as shown, you can see the camera, motion sensor, ultrasonic sensor, and thermal sensor with the facial recognition and building management system combined. So based on after upgrading any sort of sensors and camera modules, our total cost for the system was $150.42, which made it right within the budget that we were given. Next. And these are our standards and ethical issues. So for the standards, we filed the IEEE, as well as the others listed there, and our ethical issues of facial recognition accuracy and website security was implemented also, including security protocols and different authentication and user isolation purposes for our security personnel page. And Karini will finish.
These are the constraints that we've come across when building our system for both hardware and software. For hardware, some of the constraints include the accuracy of the temperature sensor being up to 95%, and also the ranges for all the sensors, including the higher temperature sensor, the ultrasonic, and the motion sensor. And also the picture resolution for our camera being 640 by 480. And also the sensitivity of the motion sensor itself. For software, As previously mentioned, some of the constraints include like over 50% of the facial embeddings being blocked by facial coverings, which was considered by upscaling the captured images and decreasing the kernel size to avoid misclassification and achieve the 98% accuracy that we showed previously. The other constraints includes the facial, like, and when an image isn't captured like straight on because it's not fully centered, so it can cause distortion. So to account for this, the facial detection algorithm had to warp the facial embeddings just again to avoid misclassification. Another one being the deep learning method was expensive computatively and taking longer prediction times. But as you can see, we were able to surpass this, and we were able to have a processing time of like less than a second. And last being that you can see the IP we gave, it wasn't a domain name because it needed a subscription fee. So like we don't have a domain name for the website. And that's it. And then on the next page, these are all the references that we use to conduct our research on our background and related work theory. So that's the end of our presentation. Thank you for listening. If you have any questions, please feel free to ask.
Yeah, can I have a question? So yeah, I want to ask that all this training use the regional convolution neural networks. So this training is based on was performed on the microcontroller, the training process, or is to use the pre-trained model?
No, so we have a pre-trained model. So the model is trained in a different environment, and it's pretty much trained on a database of 50 other people with, a few data set for each individual person. And then that model is saved onto our database, and simultaneously the system architecture will pull that information within that 1 second. And so nothing is in the microcontroller other than just it getting all the data from the individuals, temperature, motion sensors, and all of that.
Okay, so in this case, your pre-trained model that they can you just use that to perform like a testing, right? So so when you can also get the new data to fit into the pre-trained model, the accuracy I think is really good. Okay, yeah. So so how long it will take you to perform the testing? Like, what's the time? Like, do you have a time? Yeah, how is it cost any day or?
Testing wise for the software, other than time and paying somebody per hour to do it, it's not really going to cost anything.
Okay.
Testing time is very simple. So I made the model to where you can simultaneously add new people to it. So of course, there's going to be new students. You can delete old data. You can add new data. It's all simultaneously in the algorithm.
Okay, thank you. Yeah, very interesting project.
Any other questions? Thank you so much, Mendoza, Nancy, Ahmed, Anina, and Brandon. You did a great job. On behalf of my students, I would like to thank Dr. Yakos and all professors who attend today for evaluating their works. I would like to pass the control to Dr. Sultan. Dr. Sultan, the mic is yours.
Thanks, Dr. Manai. Thanks